Welcome to the Developer Journal. I am Sloan. Today we explore a fundamental shift in the industry. We are moving past the era where just adding more parameters was the primary goal. Now the focus is on extreme precision and how we actually put these massive systems to work effectively in the real world. We will examine how Anthropic is redefining agentic workflows with the release of Claude Opus 4.7. We also explore the surprising emergence of one-bit architectures that promise to make inference significantly more efficient for every developer. These changes are reshaping the landscape of modern software development and engineering roles.
Sloan, you should be watching the hardware side closely, because NVIDIA just dropped something unexpected with their Ising model family. This is a first for hybrid quantum systems, and it changes how we think about error correction. I want to see if the actual performance matches the high expectations set by their marketing department.
Vance, that concern about the hardware layer is where the real battle will be won or lost this year. It is a day of deep technical dives and strategic pivots that could define the next decade of computing infrastructure. Our journey begins with a deep dive into the newest agentic upgrades from the team at Anthropic. The shift we are seeing in Opus 4.7 suggests we have finally crossed a critical threshold for software engineering by achieving a 70% score on the Cursor Bench benchmark, compared to the previous 58%. The model demonstrates it can handle heavy workloads without constant human intervention or manual corrections. Beyond just writing code, the reduction of tool errors by 2/3 is a massive win for reliability in complex environments. When an agent can hand off multi-step engineering tasks autonomously, it moves from being a simple assistant to a legitimate member of the development team that saves thousands of hours. Business leaders will likely find the new task budgets feature most compelling because it provides necessary guardrails for token expenditures. This public beta allows companies to finally cap costs on long-horizon workflows, making the deployment of autonomous systems a predictable line item rather than a financial gamble for the department. It also reached state-of-the-art results on third-party benchmarks, evaluating high-value knowledge work in the finance and legal sectors. But while the economic implications are clear, I want to know how the actual sensory input of the model has changed to support these advanced capabilities.
The most impressive technical leap is actually found in the vision resolution, which has tripled to approximately 3.75 megapixels. This upgrade pushed computer use visual acuity from a coin flip at 54.5% to a near-perfect 98.5% when identifying objects on a screen. On the coding side, we saw a 13% performance lift across a 93-task benchmark, including 4 complex problems that were previously unsolvable. This suggests that the underlying reasoning has reached a depth where it can navigate architectural obstacles that would have completely stalled the previous iterations of this model. Engineers now have the extra high effort level, which serves as a critical trade-off tool for specialized deployments. It allows us to decide if the increased reasoning depth is worth the added application programming interface latency, giving developers granular control over how much power they actually need for a specific task. We are seeing a trend where proprietary leaders are pushing the limits of hosted intelligence through these massive agentic upgrades. However, the conversation is also moving toward how we can take these high-end capabilities and run them on our own hardware using the latest open-weight inference workflows for maximum control. Moving from proprietary clouds to local hardware sounds liberating, until you look at the actual bills for the specialized silicon required. While the 20 billion parameter model is accessible, the massive 120 billion version necessitates Hotel 100 or Alpha 100 hardware, equipped with 80 gigabytes of video random access memory. You cannot just slap old optimization tricks on these architectures and expect them to perform at their peak level. Native microscaling 4th generation floating point 4 quantization is now mandatory for these open-weight workflows, because relying on legacy bits and bytes 4-bit loading patterns causes significant performance degradation that ruins the model reasoning capabilities. Even the inference settings require a strict adherence to the OpenAI recommendations of a temperature of 1.0 and a top p-value of 1.0. If you try to modulate reasoning effort through system prompts, you can toggle between low for concise answers and high for deep chain of thought analysis during execution. We also see major friction when developers forget to include logic that strips markdown code blocks from the output stream. Without that step, the structured data extraction workflows will consistently fail at the JavaScript object notation parsing stage, especially when the tool executor framework is trying to trigger dynamic calls to external application programming interfaces.
Vance, those high-end requirements might be daunting, but the 20 billion parameter model is actually a massive win for mid-market enterprises. The fact that this smaller version can run on a standard NVIDIA Tango 4 with only 16 gigabytes of video random access memory brings advanced local intelligence within reach for smaller firms. Maintaining a coherent narrative during complex customer service or technical support scenarios is finally becoming manageable thanks to the new Harmony format. It ensures that multi-turn dialogue handling retains its context across stateful interactions, allowing the model to act as a reliable partner rather than a forgetful calculator that drops the conversation thread. When businesses can host these models internally without sacrificing the quality of the conversation, the entire landscape of data privacy changes for the better. We are witnessing a transition where the power once reserved for massive server farms is being compressed and refined for specialized, secure environments that do not require an enterprise-scale budget. But as we look toward the future of efficiency, even these 16 gigabyte requirements might start to look heavy to some engineers. We need to pivot from these high video random access memory requirements to the extreme optimization of the 1-bit frontier to see how small these models can truly get.
Using the Q10 Golf 128 format to drop memory requirements from 3.44 gigabytes down to 0.24 gigabytes for a 1.7 billion parameter large language model is a masterclass in squeezing utility out of silicon. It represents a paradigm shift in how we handle weight representation during inference. This specific quantization uses 1 bit for the sign and a shared 16-bit floating point scale across every 128 weights, which results in an effective 1.125 bits per weight. This level of extreme compression is what allows such a massive reduction in the memory footprint on the graphics processing unit. Hitting 674 tokens per second on a GeForce ray tracing Extreme 4090 is a staggering 3 times speed increase over the standard 16-bit floating point results. This throughput removes the traditional latency bottleneck for real-time retrieval augmented generation and complex structured JavaScript object notation, data extraction workflows for modern engineering teams. The deployment utilizes a specialized fork of llama.c++ with optimized binaries, specifically compiled for Compute Unified Device Architecture versions 12.4 and 13.1. By targeting these specific libraries, the system enables these 1.7 billion parameter models to run comfortably within only 248 megabytes of video random access memory.
Vance focuses on those technical specifications, but we should consider the incredible potential for edge devices that previously could not even run a basic chatbot. Running a 1.7 billion parameter model within 248 megabytes of memory means we are finally putting sophisticated intelligence into the hands of local hardware users. The support for a 32,768 token context length on such a small footprint makes these models actually useful for processing long documents. We are moving beyond short chat bursts and into a world where a tiny device can digest an entire technical manual without needing a connection to a massive server farm. This specific framework also scales up to an 8 billion parameter variant, that supports 65,536 tokens for even more complex operations. It ensures that multi-turn chat and retrieval augmented generation workflows remain reliable and fast, while maintaining an open artificial intelligence compatible server mode for seamless integration into existing enterprise software stacks. While we are busy optimizing our current silicon to these extreme limits, a different kind of compute is emerging on the horizon. We are about to witness how the industry moves from these hyper-efficient local models to the massive leap into hybrid quantum and classical systems, with the latest release from the team at NVIDIA. The introduction of the Ising model family by NVIDIA marks a pivotal moment where quantum computing steps out of the purely academic realm and into a more practical operational phase. By leveraging these first open quantum artificial intelligence models, we are seeing a dramatic shift in how researchers manage the complex hardware required for these systems. One of the most immediate benefits is found in hardware calibration, where tuning cycles that previously spanned several days are now being compressed into just a few hours. This massive efficiency gain is driven by a vision language model that understands the intricate state of quantum processors without the constant manual intervention of a physicist. With major institutions like Harvard and the Fermi National Accelerator Laboratory already adopting this framework, it feels like we are witnessing the birth of a unified operating system for the quantum age. This level of institutional buy-in suggests that the industry is finally ready to standardize how we interact with and correct these fragile systems. Vance, I am curious how these speed gains actually manifest when we look at the specific libraries and the hardware interconnects that NVIDIA is using to pull off this level of coordination. Is this truly a breakthrough in performance, or just a very clever optimization of existing software tools that were already available to researchers?
Looking at the benchmarks, the 2.5 times faster performance compared to the current industry standard library known as pi matching is quite significant. This is not just a minor software tweak, but a fundamental reimagining of how we bridge the gap between classical graphics processing unit kernels and the quantum workflows using the Q2Q programming model. The Ising decoding component is distinctive because it employs three-dimensional convolutional neural networks to provide real-time error correction. By achieving 3 times higher accuracy than previous standards, this system addresses the critical low-latency communication needs that are necessary for active error correction during a quantum computation, which is notoriously difficult to manage. NVIDIA is solving the hardware bottleneck with their NVQ-Link interconnect, which enables the extremely fast communication required between the graphics processing unit and the quantum processing unit. This tight coupling allows classical algorithms to supervise quantum states in real time, which is the only way to make these noisy intermediate-scale quantum devices actually reliable. While these scientific breakthroughs are reshaping the high end of compute, we must also track how these sophisticated stacks are being repackaged for broader enterprise use. We should pivot now to the commercial and security implications of these rapidly advancing artificial intelligence stacks as more players enter the voice and speech processing market with new tools. The competitive landscape for voice services is shifting rapidly as the artificial intelligence company enters the enterprise market with a clear intent to disrupt. Their speech-to-text engine reports a 5.0% error rate on phone call entity recognition, which is remarkably low for the industry today. That performance is a major threat to 11 Labs, which sits at 12.0%, or assembly artificial intelligence at 21.3%. By supporting legacy telephony standards like micro-law and alpha-law, they are clearly targeting the trillion-dollar global call center infrastructure, rather than just modern web applications. The implementation of a text-to-speech WebSocket streaming endpoint is another deliberate technical choice for high-performance needs. It allows for unlimited text input length and immediate audio playback before the full processing is finished. This minimizes the perceived latency that usually kills the user experience in automated voice systems. We also see built-in inverse text normalization, which is a huge hurdle for automated transcription in professional settings. This feature automatically converts spoken phrases into structured data, like $167,000. It streamlines the output from medical and legal documentation, which requires high precision for structured records.
Vance, your point about structured data highlights why these tools are becoming essential for the modern back office. While the accuracy is impressive, the human resonance of a voice determines if a customer feels heard. Using specific tags like whisper and laugh to reduce emotional flatness represents a major shift for enterprise bots. Consider how Starlink is already utilizing this entire stack for their customer support operations to handle automated troubleshooting. By combining real-time transcription with more expressive speech, they are bridging the gap between a frustrating automated response and a genuinely helpful assistant. It changes the narrative around how businesses manage high-volume support. The inclusion of speaker diarization and word-level timestamps also signals a push toward highly regulated industries like law and medicine. Providing that level of granular detail allows organizations to maintain strict records without manual oversight. It is about creating a seamless bridge between a spoken conversation and a permanent digital archive. As we see these powerful artificial intelligence tools weave themselves into the fabric of corporate operations, we have to confront the vulnerabilities they introduce. The rush to integrate these sophisticated voice and speech stacks is creating a massive security debt. We need to look closely at how authorization failures are exposing these systems.
The Vercel breach that occurred on April 19, 2026, serves as a sobering reminder that simply having valid credentials is no longer a sufficient security signal. In this specific incident, a compromised third-party tool utilized a valid Google Workspace open authorization application to impact hundreds of users across multiple organizations. What makes this situation particularly alarming from an engineering perspective is that the attackers did not trigger a single standard policy violation alert or secret rotation protocol. They operated entirely within the boundaries of established permissions, while effectively bypassing the security controls we have spent years refining for human users. This demonstrates that the principle of least privilege is fundamentally insufficient when dealing with autonomous agents that can perform high-value data searches within authorized scopes. If an application is granted access to a Google Drive, an attacker can still cause massive damage without technically overstepping their bounds. We are witnessing a structural gap in what we call Layer 3 authorization, which verifies access grants, but fails to monitor actual application behavior. There is a desperate need for a transition toward Layer 4 behavioral trust, which focuses on detecting what is known as scope adherence drift.
Vance, the structural gap you just described suggests that the industry is currently flying blind once an agent passes the front door. This breach highlights a massive disconnect between identifying who an artificial intelligence agent is and understanding what it is actually doing to our sensitive internal systems. The market for trust scoring and continuous anomaly detection is about to explode as enterprises realize they cannot deploy powerful models without a safety net. Solutions like Agent Layer are becoming the new standard because they provide the visibility required to identify supply chain compromises before they turn into catastrophes. We are moving toward an era where the reputation of an agent is just as important as its performance or its raw intelligence. Businesses will soon refuse to integrate any tool that lacks a behavioral trust score because the risk of a silent data exfiltration is simply too high for modern compliance. As we conclude this session, it is clear that the conversation around innovation is shifting from pure capability to robust defense. Final wrap-up on how precision and security are now more important than raw model size in the race to deploy autonomous agents safely across the enterprise.
The shift toward agentic task budgets in the latest Claude Opus 4.7 update reveals how much we are moving toward resource-constrained precision. At the same time, the recent security breach at Vercel proves that even the most sophisticated open authorization layers can crumble when we fail to monitor the behavior of autonomous systems.
Vance, your observation regarding those specific failures underscores the fact that raw parameter counts are no longer the primary measure of progress in our field. We are entering a phase of high-precision operationalization, where the focus has moved from how large a model can grow to how effectively it can be governed and safely deployed. As you head back to your local environment, consider how these shifts in security and efficiency will change your next deployment. Thank you for joining us today on the Dev Journal for this deep dive into the engineering of the future. We will see you tomorrow to break down the next wave of technical evolution.